Has the theory group elected to maintain its reputation for the severity of its seminars?
I even Isha has mellowed out a lot, and the rest of us are not. We ask questions.
Yeah, no, I mean,
go for the jugular. I don't know. It depends on what happens.
It depends on what I say. Yeah, I mean, it's really up to me, right? How it goes.
There are topics that are sort of like more likely to result in sort of tomatoes being thrown, metaphorically speaking, but I think it's unlikely to be able to today.
You never know. Never say never.
Okay, I think you're set. You connected to the Zoom, I guess.
Connected to the Zoom. My audio is on.
It's going to record it. Hopefully, that should be automatic. I'm going to step away for a minute.
Of course. Yeah, absolutely.
Next week. But I think yeah. I think there's a thesis because I want to go to a meeting.
Are you feeling about the future of dark matter this morning?
How am I feeling about
it?
Yeah. So I don't know, maybe a little bit. Get a good night's sleep.
I looked at the atomic results. It is impressive.
Yeah, it's pretty crazy. Yeah, I wasn't expecting it. And I emailed the corresponding author like that morning. I was like, wow, amazing. How did you guys do so much better? Yeah, like bullet. And they intend to, the expectation is that they're going to significantly improve as well, because they did a lot better than they thought they were going to do. And this is like, I don't know what the timeline for better is, but I think it's like, a year or something. Okay. Like it's a very short timeline. Yeah.
Wow. Okay. Exciting times.
Could we start? Okay, so it's 12:30, and we're very lucky to have Nathaniel here. He gave us a wonderful colloquium yesterday, and today he'll tell us about higher symmetry in phenomenology.
Great. Thanks very much. Thanks for being willing to hear me again. I promise today there will be neither colliders nor muons, but hopefully some other aspects of interest, broadly speaking, both in QFT and phenomenology. So this talk is based on both some work that I finished last year with Marius Kantor, who is a graduate student of Ken Van Tilburg's at NYU, and also work in progress with people in Santa Barbara, Amalia Madden, who's a new postdoc at KITP, and Dan Hayek, who's a graduate student of mine. Dan, it's sort of as a testament to some of the stuff I'll be talking about today. Dan actually started his career as a condensed matter theory student, and it's really a testament to sort of the way in which the modern language of generalized symmetries has brought these communities together in very interesting ways. So just to explain a little bit the backdrop of my title slide, I think broadly speaking, for particle phenomenologists or particle theorists, we've undergone quite an evolution of the field over the last 15 years or so. The discovery of the Higgs boson and nothing else at the LHC, also coupled with null results in a wide range of terrestrial and astrophysical experiments, really sort of forced a bit of a paradigm shift in our thinking about the standard model in physics beyond the standard model. And I'd say where we've come over the last decade, particularly, is to recognize that, for many years, we were living under a bit of a theoretical lamppost where our priors for the sorts of physics that might lie beyond the standard model were somewhat narrow. And they certainly focused our attention in particular ways. But now that we've, I think, recognized that some of those priors were maybe not realized in nature, now we've sort of looked outside the lamppost and realized, there's a vast universe of possibilities around us. That certainly has been true in the interface of particle theory and experiment. We have a real flowering of particularly small scale experiments over the last decade. But one of the underlying messages I want to articulate today is also that the same is true in the context of theory. That we're sort of in a golden age of quantum field theory, both in condensed matter physics and high energy theory. There have been dramatic developments over the last 20 years in our control of quantum field theories. And we should also be able to take advantage of that as we think about fundamental physics and physics beyond the standard model. So really the message today is trying to convince you that there are some directions in theory space that are also outside the normal lampposts that particle theory has been operating in. And I'll try to convince you of why it might be interesting. This talk is sort of composed in 3 parts because I want to leverage some of the newer developments in quantum field theory. That involves exploring aspects of the space of generalized symmetries, but I don't want to presume familiarity of generalized symmetries. Actually, out of curiosity, how many people in the audience feel like they have a good working understanding of, say, higher form symmetries? Okay, so a few people, so I hope you'll forgive me, be patient for the first couple of slides as I try to convey some background to the rest of the audience. After giving that background to everyone else, then I want to give you 2 examples where generalized symmetries can be brought to bear productively on questions of physics beyond the standard model. And that will then connect all the way to interesting opportunities in experimental data. Okay, but to start with a general guide, so again, apologies to the experts, especially for the slight imprecisions that I will commit here. So to give you a sense of what generalized symmetries are about, or particular higher form symmetries, which will be the focus of most of the talk, the first thing I just want you to do is think of a slightly new way of talking about familiar old symmetries or ordinary symmetries, global symmetries in quantum field theories. We'll be primarily operating in 3+1 and 4+1 dimensions today. And so all I want you to do, we're very familiar with the idea that if we have, for example, a conserved global symmetry, that we can construct a unitary operator that implements a symmetry transformation. And we do that by taking whatever our conserved current is, taking its time component and integrating it over a spatial surface. And so the only thing I want you to generalize is to go away from that strict definition of a unitary to instead imagine constructing a similar object where now instead of having it be on a spatial slice, you just pick some codimension 1 manifold on which you can integrate the normal component of your conserved current. Okay. And so, for every group element that you might have of your global symmetry, you can construct such an operator where the element is labeled by some parameter. And now you just, instead of integrating the time component of your conserved current, you're integrating whatever component is normal to this codimension 1 surface. All right, and so, we'll no longer exactly call that a unitary because it extends in the time direction, but we'll call it a symmetry defect operator. For our purposes, that's just jargon. And it has nice properties that recapitulate the structure of the global symmetry, right? We're just talking about normal, ordinary global symmetries. We haven't done anything fancy yet, but I want to get familiar with this idea of how we can discuss the symmetry in terms of topology, and then we can take a step towards generalizing it. Okay, so these symmetry defect operators, some of the properties they obey, they recapitulate the group multiplication law in the sense that if I form 2 of these symmetry defect operators for 2 different group elements on the same surface, that resulting object behaves as the corresponding symmetry defect operator for whatever I would have gotten from the group product of the two elements. Okay, so it recapitulates the multiplication table of my group. Also, they're topological in the sense that they're invariant under smooth deformations of the surface that don't cross charged operators. And the way you can see that is you can just say, imagine taking one of these symmetry defect operators and the symmetry defect operator for the inverse element on a slightly different deformed surface. So maybe the original surface and the deformed surface. This encloses some area in between. Bring them together. And if the surface is topological, when I bring these two together, the inverse defined on a slightly different surface should still act like the normal group inverse. Okay, so we can check that that's true. Indeed, it is, because as I bring these things together, what I get is proportional to the integral of the divergence of the current in this area bounded by the two surfaces. And since the symmetry is conserved, then of course this just gives me back the identity. And so it tells me that the inverse, the symmetry defect operator for the inverse element defined on the slightly deformed surface acts just like the inverse defined on the original surface. So these symmetry defect operators don't depend on small deformations of the surfaces on which they're defined. And then finally, they do what we normally expect of unitaries acting on charged operators. If we, in some sense, pull one of these symmetry defect operators past a charged operator localized at a point, that is to say, we imagine deforming the surface on which we define the symmetry defect operator, and the deformation takes us past the location of a charged operator. The effect of that is to implement the symmetry transformation that we would expect on the charged operator. Okay, so this just promotes our normal thinking about global symmetries into something that we can discuss using the language of topology. And you could recapitulate everything we're used to saying about ordinary global symmetries in a quantum field theory in terms of the construction of these symmetry defect operators and their relation. So the reason I want to say that, that's just using new language to talk about familiar things. But now you can also use that then to take a step into less familiar objects. Although many of these ideas definitely predated by considerable amounts, this paper in 2014, really, I think the modern language of higher form symmetries and generalized symmetries was kicked off in the seminal paper by Gaida, Kapustin, Seiberg, and Willett, where they suggested, that we can take this idea of defining global symmetries of a quantum field theory by its symmetry defect operators and their relations. And then we can use that also to generalize the notion of these ordinary global symmetries. And so the first direction really that was generalized, and the one that we'll lean on most today, is to go from ordinary zero-form symmetries, where the charged objects are operators localized at a point, to imagine instead having symmetries that act on extended objects. And the way that that would work is for our ordinary symmetries that act on charged operators defined at a point, our conserved currents are one forms. Now we could instead imagine defining appropriately higher form symmetry currents that are conserved in the appropriate way. And we could imagine then constructing symmetry defect operators. Now, of course, as the degree of the conserved current goes up, the surface, the dimension of the surface on which we define the symmetry defect operator goes down correspondingly. So for example, the simplest generalization away from an ordinary zero-form symmetry would be a one-form symmetry where we have a two-index conserved current. And the symmetry defect operator would now be some codimension 2 surface of my spacetime. Okay. But you could define appropriate symmetry defect operators in exact analogy with our ordinary symmetries. And this now allows us to imagine defining the operation and action of symmetries now that have sort of higher form conserved currents. Now, of course, the Coleman-Mangela theorem tells us these can't be symmetries of interacting particles in d greater than 2, right? If you're ever teaching QFT and you're teaching people the Coleman-Mangela theorem, everyone takes, Witten's nice paper and says, oh, the theory of scalars, I can construct infinitely many conserved currents, but they can't have any point particles charged under them. So in fact, we know that these symmetries can't act on interacting particles, but there's a loophole in Coleman-Mangela, which is they can act on higher dimensional charged objects. And indeed, the sense in which, as the degree of the conserved current goes up, the codimension of the symmetry defect operator goes up, so the dimension on which it's defined goes down. The dimension of the operators, the objects charged into these symmetry defect operators goes up, so that there's always a well-defined linking between the symmetry defect operator and the charged object in whatever your space-time dimension is. One thing you learn immediately from this is p-form symmetries. So higher form symmetries, as soon as you step beyond the ordinary case of p is equal to 0, they're necessarily abelian. And a simple way to see that is if you just imagine the case in 3 dimensions, where you took, for example, a one-form symmetry. So in that case, the symmetry defect operators would be defined on lines, and the charged objects would also be lines. And you can imagine a situation where, for example, there's a charged line operator, and you construct two symmetry defect operators corresponding to different group elements. Now, of course, if you pulled both of these symmetry defect operators past the line operator, they would implement first the G1 transformation, then the G2 transformation. But since they're topological, I can also imagine bringing the G1 SDO down, stretching it out, and pulling it back up. And now, if I pulled these operators past my line operator, of course, it would first implement G2 and G1. And if the symmetry defect operator is topological, these have to be the same, and so the symmetry has to be abelian. And so if you're a particle physicist, at this point, you may be disappointed, right? Because much of the richness of particle theory over the last 30 years has lived on, the richness of non-abelian phenomena. But hopefully, as I'll convince you today, even the restriction of these higher form symmetries to abelian groups has an incredible amount of power for us. Okay, just to make it very concrete for systems, that we're used to thinking about in particle physics, just to give you a couple of classic examples in 4 dimensions. And we'll come back to these examples in some of the phenomenology that I'll develop later in the talk. Maybe the simplest example to think about in 4 dimensions is what we call Maxwell electrodynamics, which is just electrodynamics without any charged matter. And so there's a natural candidate for 2-index conserved current, which is just the field strength tensor itself. In the absence of charged matter, you would say this is a current that's conserved by the equations of motion. And as we know, it's easy to write down possibly conserved higher form currents, but the question is, what are the charged objects? And the idea is the charged objects in this case are the Wilson lines of the theory. So even though I don't have dynamical charged matter in Maxwell electrodynamics, I can think of the Wilson lines as being the world lines of infinitely heavy charged particles. And these are the things that in fact transform appropriately under the higher form symmetry transformation. Of course, there's sort of 2 interesting field strength tensors in Maxwell electrodynamics. One is the original field strength tensor, and the other is its dual. And so in fact, there's a second one-form symmetry of Maxwell electrodynamics, which we call magnetic one-form symmetry. It's just constructed out of the dual field strength tensor. And this is conserved in the absence of monopoles by the Bianchi identity. And just as the electric one-form symmetry acted on the world lines of electrically charged particles, the magnetic one-form symmetry acts on the world lines of magnetically charged particles, or the H'tooth lines. Okay, 2 other examples that we'll come back to later. You can also think about periodic scalars or axions if you're a particle theorist. So that's something that has some periodic shift symmetry. So we're used to thinking about the shift symmetry of the axion as being the thing that we mostly care about. But actually, an axion has another higher form symmetry. It has a 2-form symmetry. The current, which is a 3-index antisymmetric tensor, is sort of trivially conserved just by antisymmetry. But again, the question is really, what are the charged objects? And the answer here is that the charged objects are the world sheets of axion strings. Those now are appropriately charged under this 2-form symmetry. The last example is Yang-Mills, where we don't have any matter charged under the center. So of course, center symmetry has long played a role in our understanding of confinement. And now in modern language, we recognize that the center symmetry of Yang-Mills is just an example of a 1-form symmetry. It's not a continuous symmetry, it's a discrete symmetry. So for example, for SUN, the center would be Zn. So it's a Zn 1-form center symmetry. And the charged objects are just Wilson groups, transforming the different representations of the group. Okay, so if you're a particle physicist, this idea of higher form symmetries, it may seem needlessly abstract, but the first takeaway is that these symmetries live in all of the theories that we care about and all the theories that we've cared about for decades. And so there have to be things we can learn from them. Now, these things are not going to come out and hit you in the face because we've understood these 3+1 dimensional field theories for decades. We haven't missed a lot. Okay, so anything new that we learn by thinking about the language of generalized symmetries is going to be subtle, but hopefully I'll convince you today that there's still some interesting things that we stand to gain.
For the axiom example,
yeah,
it's hard to dual to a 4-form.
Yeah.
And so is that equivalent to this 2 forms?
Yeah, you could think exactly. You could.
Because this is the
yes.
Guia-Diwali.
Yes. So I'd say there are some things that we've known about for 20 years in particle physics that Guia and others and Nemanja had been trying to convince us of 20 years ago that we maybe lack the systematic language for. You could actually, it's some fun to go back to Guia's papers from 20 years ago and rewrite them in a language of generalized symmetries. Absolutely. Yes, absolutely. Okay, I want to mention 2 things just in this general warm-up before we get to phenomenology. And this is, in the broader scheme of how you sort of make generalized symmetries relevant to particle physics, I think it's helpful to remember that particle physics is not the art of exact symmetries. It's the art of spontaneous and explicitly broken symmetries, right? Particle physics sort of is the study of approximate selection rules that that follow in the presence of broken symmetries. And so it's useful to ask, in the same way that we try to understand explicit and spontaneous breaking of ordinary symmetries, how we should think about the explicit and spontaneous breaking of higher form symmetries. So let's start with spontaneous breaking of higher form symmetries. And these p-form symmetries for p greater than 0 can be broken just like ordinary 0-form symmetries. And there's a Goldstone's theorem that also applies. So now they should give rise to p-form Goldstone bosons. The criteria for symmetry breaking, to develop the criteria, it's helpful to sort of think about the criteria we would have for making a precise statement about spontaneous breaking of a 0-form symmetry. And there we would say, if we had some charged operator in the 0-form symmetry, if we take two such operators at large separation, that expectation value is just some product of non-zero expectation values for the two operators. But really what this means is that this depends in some sense only on the points on which the operators lie and not on their separation. Okay. And so you can take that criteria and now apply it to higher form symmetries. So now we can also imagine taking charged operators, for example, in the case of a one-form symmetry, a Wilson line in the electric one-form symmetry. Now if it gets an expectation value that depends only on the surface on which the charged operator is defined, that's the equivalent criteria that we had in the 0-form case. And so indeed, if you have, for example, a Wilson line and its expectation value scales like the exponential of the line itself with the curve on which it's defined, that would satisfy the criteria for spontaneously breaking the one-form symmetry. And so just to come back to the four-dimensional Maxwell theory example, when you open Peskin and Schroeder or Mark Czernicki's QFT textbook as a student, and you have to compute the expectation value of a Wilson loop to get the Coulomb potential, right? You find that indeed in the Coulomb phase, Wilson loops have perimeter law scaling, which is consistent with this criteria for spontaneous symmetry breaking. And so we'd say, in fact, the electric one-form symmetry in Maxwell electrodynamics is spontaneously broken, and there's a Goldstone boson, and that Goldstone boson is the photon. And I should emphasize, this language sort of has arisen, since the 2014 paper and the definition of higher form symmetries. But this idea that the photon is a Goldstone boson of a spontaneously broken one-form symmetry actually dates back to much before the mid 2014s. And that's sort of nice. It's interesting as a particle physicist, we are interested a lot in light degrees of freedom. We understand, for example, the lightness of scalars if they're Goldstone bosons of spontaneously broken ordinary symmetries. And it's at least interesting that you can also think about photons as being Goldstone bosons now of spontaneously broken one-form symmetries. I also want to say something about explicit breaking of higher form symmetries, because here there's a very interesting contrast with ordinary symmetries. If you have an ordinary 0-form symmetry and you explicitly break it, even if it's far in the ultraviolet of your theory, that has dramatic consequences in the infrared. For example, if we have a spontaneously broken ordinary symmetry that we also explicitly break by some parameter, that gaps the Goldstone boson that we would have had if the symmetry were exact, right? So there's dramatic effects in the infrared. The consequences of explicit symmetry breaking for higher form symmetries are much more subtle. And so I want to focus, because it'll be relevant later in the talk, again, on this case of Maxwell electrodynamics and its electric one-form symmetry. And here the idea is charged matter, not matter that's charged under the one-form symmetry, but matter that was charged under the gauge theory, under electromagnetism, that would explicitly break the electric one-form symmetry. Okay. And there's sort of two ways of seeing that. So certainly if I add charged matter to my Maxwell electrodynamics, now the equation of motion tells me this thing that I thought was my conserved 2-index current is no longer conserved, right? There's a matter current that appears on the right-hand side of the equation of motion. And as soon as the current is no longer conserved, the symmetry defect operator that I use to define the symmetry is no longer topological. And so I can no longer define the action of my symmetry through these topological objects. Another way to see it, maybe it's more intuitive, is once we have dynamical charged matter, now I can end Wilson lines, right? And Wilson lines can end on a fluctuating charge degree of freedom. And so now it's no longer the case that my symmetry defect operators always have to link the Wilson lines, right? If I have an endable Wilson line, I can now just unloop a symmetry defect operator around the end without crossing it. So it doesn't affect the transformation, and therefore there's really no longer a well-defined symmetry. Okay, so as soon as dynamical charged matter appears, that means the symmetry is explicitly broken. But now you can ask the question, what if I think in the framework of an effective field theory, if I go below the mass scale of some charged particles, I should integrate them out, and I should operate in a low energy field theory in which I only have soft imprints of that explicit symmetry breaking. And indeed, again, in the case of a 0-form symmetry, if we explicitly break the symmetry in the UV, there's dramatic effects in the infrared. But in the case of, for example, this one-form symmetry, if we explicitly broken it in the UV because we have some massive charged matter, the effects in the infrared are much more subtle. So in particular, right, you could just imagine the exercise of taking electromagnetism with a charged fermion and some finite mass, integrating it out and getting some effective field theory, which would be the Euler-Heisenberg-Lagrangian. And you might say, looking at the Euler-Heisenberg-Lagrangian, oh, indeed, my 2-index antisymmetric current is no longer conserved because now I have all of these terms on the right-hand side coming from these irrelevant operators. But the form, of course, of the terms on the right-hand side is suggestive that you can simply move them over to the left-hand side and define an improved current, which is still conserved. So even in this case, although I've explicitly broken the one-form symmetry in the ultraviolet, I still have a perfectly well-defined conserved one-form symmetry in the infrared. So it's an emergent symmetry, and it's an emergent symmetry of extremely high quality. In fact, because local objects, local operators are not charged under the one-form symmetry, there's nothing in the low-energy EFT that violates the symmetry. And so you might think, in fact, that this emergent one-form symmetry becomes exact as soon as you pass below the mass scale of the charged particle. Now, it's not quite that good, okay? If you had an exact symmetry, as soon as you'd integrated out these massive charged particles, it actually wouldn't even be very interesting. Instead, if you ask the right questions, you can see there are still imprints of this explicit breaking in the UV in the infrared, but the imprints are very subtle. So, for example, the things that are charged under the higher form symmetry are the Wilson lines, and you would expect to see imprints of UV symmetry breaking in the dynamics of the Wilson lines themselves. And so, indeed, if you try to, for example, describe the effective theory of Wilson lines in the infrared in this theory, you see that there are some imprints of the fact that you have very heavy charged particles. In particular, there's exponentially small effects that signal that the symmetry is broken in the ultraviolet. Okay, so the takeaway here should be that higher form symmetries are often emergent. The things that break them in the UV are things that are charged under the underlying, for example, gauge symmetry that gives rise to the global symmetry. As we go to the infrared, they become extremely good symmetries. In fact, typically they're exponentially good. And that's very much in contrast to ordinary symmetries that are explicitly broken in the UV.
Oh, sorry.
Yeah.
I mean, I want to interpret this. Okay.
Yeah.
Right. So we say this, there's an emergent,
Yeah.
that symmetry below scale is in the context I'm doing, really integrate out this heavy formula. So I don't see any existence of that, right? However, my low energy excitation of photon, for instance, I still understand there exists a physical charge object, even though I don't probe that scale directly.
Well,
my vacuum is not trivial. I still break that.
Indeed. So in the EFT, what you see is if you, for example, want to write down some effective action that allows you to compute expectation values of Wilson lines in the IR, what you'll find is that that's given that what appears in that effective theory are terms that have Wilson coefficients that go like e to the minus mass of a charged particle times length of the Wilson line. And so the intuition is for sufficiently long or sufficiently excited Wilson lines, that's, that ultimately is able to pair produce charged particles and antiparticles out of the vacuum. So that's what this exponential suppression comes from. Yeah.
There's a potentially interesting subtlety here, which is that everything here makes complete sense for spontaneously broken. And then there's not so much subtlety. But if the one-form symmetry is not spontaneously broken, things are.
Yes, and so for a wonderful exploration of that, I refer you by a lovely paper by Alexei, which I think is also, to my knowledge, the only clear articulation. This and then a paper by Iqbal and Maghribi. Those are sort of the only two clear articulations of how you should think about these exponentially small effects in the infrared. In the examples, phenomenological examples I'll give you in a few minutes, there are other ways that you can actually start to see the same things. They, again, are exponentially small, but this is just sort of meant to be a general discussion.
Okay. I think it's sort of the same question, but obviously, if my theory is confined in the infrared, adding an alpha matter changes,
Yes.
there's no longer small perturbation.
Absolutely, indeed. So this entire discussion assumes that I'm in the spontaneously broken, I'm in the coolant phase of the infrared, and indeed, there's the basically up until 2023 in all discussion in 3+1 dimensions, this assumption was implicit, and then there's this very nice paper by Alexei and Ted that made that assumption very, very explicit. And the consequences being
restrictions on the low energy coefficient C if you integrate out the actual particle, right? Like sign and so on. But if I remove these restrictions, are there any constraints from the low energy?
So there's a whole undeveloped physics program of describing and characterizing the effective field theory of the Wilson loops and applying constraints on their Wilson coefficients in analogy with, for example, positivities we currently do in local EFTs. to my knowledge, this is not, this is something that a couple of groups are working on, but is not mature.
There's very little work. on that.
Very little
It's a
work.
very interesting question, but it's very hard.
Yeah. I should say the best way to make progress on this, to try to make it concrete, is really to work on the lattice, where the higher form symmetries act nicely on the links. And this idea that you get exponentially small effects of breaking in the infrared is captured by the hopping parameter expansion. So that's pretty much the only place where we are able to make some progress. Okay. If any of you have children between the ages of 3 and 10, you'll recognize this. We're not only in the golden age of quantum field theory, we're also in the golden age of children's television. But okay, there's a children's TV show called Bluey, and there's a character called Unicorse in Bluey, and Unicorse's slogan is, "Why should I care?" And the reason I'm putting Unicorse here is, if you're a phenomenologist, okay, this maybe is a very nice discussion of the existence of these symmetries. But again, particle phenomenologists have lived most of their lives without knowing anything about generalized symmetries. And so the question is, why should we really care? What is it that we stand to gain? And just to advertise, there's been actually a broad spectrum of work in the last couple of years, really trying to bring these new developments in generalized symmetries to bear on problems of particle physics. I just want to flash some of them here. Some of them are relevant to what I'll talk about later, but just in the interest of advertising. In particular, again, there's been very nice work coming out of University of Minnesota that has very interesting implications. And if you're a particle physicist and you'd like to know more about generalized symmetries in a language that's friendly to particle theory, there's a very nice review by Daniel Brennan and Sung-Woo Hong that attempts to make that bridge. Okay, but what I want to do with the rest of my talk today is give you now 2 examples where I think we really do stand to gain quite a bit from bringing the language of generalized symmetries to bear on problems of particle phenomenology. So the first one has to do with axions and the axion quality problem, and the sense in which higher form symmetries allow us to really robustly understand how we can have high quality solutions to the strong CP problem. Okay, since it's a very broad audience, just to briefly state what the axion quality problem is. I should say axions, if you're a particle theorist these days, especially in the US, basically every particle theorist is working on axions in one way or another. The reason we care about axions is, we're trying to explain why the electric dipole moment of the neutron is very consistent with 0. And that tells us that the theta parameter of QCD is less than 10 to the minus 10. This is a surprise because in general, we'd expect it to be take some arbitrary order 1 value. And the nicest solution we have is an axion as originally articulated by Peche and Quinn and Wilczek and Weinberg, and then explicit models being built subsequently by a number of people, including people here at Minnesota. And so the idea, of course, is that the axion, at the minimum of its potential, relaxes away the theta parameter of QCD. The simplest way to understand how this works is, in the sort of canonical models of axions, the axion is a Goldstone boson of a spontaneously broken global symmetry, or Peche-Quinn symmetry. So it's just the phase. If I had some scalar and requires an active expectation value, the axion would just be the phase. And we imagine that Peche-Quinn symmetry is an exact global symmetry up to the QCD anomaly. And so, of course, QCD then will give a potential to the axion consistent with the periodicity of the axion. And when you combine this plus potentially a bare theta term of QCD, the minimum of the axion potential cancels off the bare theta contribution. And so the axion then neutralizes the theta term and allows us to understand why CP is approximately preserved by the strong interactions. Okay, so that's why we care about it so much. But of course, there's the dirty secret here is that we've assumed that this Peche-Quinn global symmetry is an exact symmetry up to only the QCD anomaly. And so, of course, we could also imagine, as with any global symmetry, we could imagine it's violated by other effects, which we could parameterize by some irrelevant operators. So, for example, you could imagine writing down some operators in the potential that depend on this Peche-Quinn scalar, which have some dependence on the fields that's inconsistent with the global symmetry. And of course, they come with some arbitrary Wilson coefficient, some arbitrary phase. And depending on the degree of these operators, they're suppressed by some ultraviolet scale. And now when you, of course, go and you break the Peche-Quinn symmetry, these give additional contributions to the axion potential, which are not aligned with the minimum that would cancel off the theta term. And so in the presence of these operators, in general, the axion settles at a place where the overall effective theta term is non-zero. And the fact that we have such strong bounds on theta, again, from the neutron EDM and other experiments, means that we're exquisitely sensitive to irrelevant operators of this form. So for the most part, in particle physics, if we have irrelevant operators suppressed by the Planck scale, they have absolutely no implications for experiment. But because we have such good bounds on the theta parameter of QCD, in fact, if the scale of spontaneous breaking the Pacheco symmetry is sort of in the range of 10 to the 9, 10 to the 11 GeV that we have other reasons to believe it should be, and these operators that break the global symmetry are suppressed by the Planck scale. In fact, these operators, if they're anything between dimension 5 and dimension 10, even suppressed by M Planck, those are inconsistent with the smallness of the Newton EDM. Okay. And this isn't just this is sort of a naive effective field theory expectation, but in fact, if you try in toy models of quantum gravity coupled to this theory, try to parameterize the effects of quantum gravity, you indeed find that these effects are generated and they're problematic. Okay. So this
is there any quantum gravity calculation?
Well, I mean, so it's semi-classical calculations where you basically you're summing over different topologies. There are various wormhole contributions.
Is that clear that it will be like the power suppressed, not exponential?
So indeed, so there's a whole history which I don't want to go into, right? The original calculations where you actually you fix the axion background, you get exponentially small effects. Then when you realize that you can't fix the axion background, and you do the calculation again, you find what, effectively speaking, translate into power law effects. So there's some very elaborate, not the point of this talk, but absolutely this has been explored in some detail. And generically speaking, the naive effective field theorist concern turns out to be borne out in sufficiently careful calculation. That's okay. Up to the fact that we, of course, don't have a completely satisfactory theory of quantum gravity, but the semi-classical regime is reliable for this calculation.
In the one solution that I know is that I think it was Linde Kalash, they didn't actually include the radial mode.
Yeah, that's right. That's right.
And then if you include the radial mode, you actually get a logarithmic effect, which ends up being powerful.
Yeah. So exactly. So and that's what okay. That's
exactly.
In slightly more detail what I was alluding to in particularly the follow-up papers to the original Kalash-Linde paper. Okay, so this has inspired a lot of model building solutions. For example, you can imagine the axion, instead of being a Goldstone boson coming from some elementary scalar, there's some composite degree of freedom, so that naturally elevates the order at which these operators appear and gives you more suppression. They could be, for example, discrete gauge symmetries. But at the end of the day, any model building that you do to understand the axion quality problem, complicates what was otherwise a beautiful and simple solution. And certainly one of the things we've learned from the last decade of particle physics is once your models get too complicated, it seems like you're asking too much of nature. There is, though, a direction that has been, I think, is very appealing if you want to understand where you could get axions of sufficiently high quality in nature, which is rather than thinking of the axion as coming from the phase of some complex scalar, you could also think about axions that arise in the compactification of higher dimensional theories, in particular from the compactification of higher dimensional gauge degrees of freedom. So this has a very long history in string theory, starting in the mid-'80s, the recognition that in string theories you typically get many axions. But what I want to emphasize today is you can also just understand the story purely with field theory in an extra dimensional setup. And this is valuable for lots of ways. We don't have to make any reference to the theory of quantum gravity. We can simply understand the phenomena in language of field theory. And this also is a place where generalized symmetries allow us to understand in a very precise way what's going on. Okay. So just the simplest toy model to think about where axions can come from in an extra dimensional context is you can just think of an abelian gauge theory living in 5 dimensions, and we're just going to compactify the 5th dimension on a circle. Of course, for realistic phenomenology, you might want to compactify it not on S1, but on S1 mod Z2. That won't have any important consequences for the things that I'll tell you. If you're curious about what that does, we can talk about it later. But for simplicity, I'll just think about compactifying this extra dimension on a circle. Okay, so to get an axion, we start in the 5-dimensional theory where we have our U1 gauge field. I'll use C to refer to this 5-dimensional gauge field. We also, of course, to make this a toy model of an axion coupled to QCD, we need a non-abelian group, which will play the role of QCD in 4 dimensions. And then there has to be something that will give us the axion coupling to QCD so that when QCD confines, we generate the axion potential that we need to solve the strong CP problem. Okay, and so that will have the form in 5 dimensions of some trans-Simons-like term. Now, when we compactify in a circle, you can pick some coordinates in which this 5-dimensional gauge field decomposes into a four-dimensional vector and a fifth component, which is going to be our axion. In particular, the integral of that over the circle direction, now that gives us a periodic scalar in 4 dimensions, which is precisely suited to be the axion. So by dimensionally reducing our 5D theory on the compactification on a circle, we end up with a 4-dimensional effective theory that consists of an axion degree of freedom, came from the 5-dimensional vector. We have a 4-dimensional QCD-like group. We have the coupling between the axion and the QCD field strengths. There also, of course, in the ... lives a whole tower of Kaluza-Klein excitations. As Tony and others emphasized, contributions from those excitations, for example, the axion potential, are very interesting, but that won't be my focus today. And the decay constant of the axion in this setup descends from the parameters in the extra dimension. In particular, it depends on the radius of the extra dimension and the gauge coupling of the 5-dimensional gauge theory. Yeah.
Wait, for the night question, why don't, so you have theta from the U1 field, from dimensionally reducing, from the fifth component.
Yeah.
Why is there not an analogous parameter for the non-linear field?
Indeed, so now, good, so there's absolutely, so now if I dimensionally reduce, there are many components of the Kaluza-Klein reduction of the SUN group. Some of them are set to 0. Actually, there's just a useful choice of the 5-dimensional gauge that sets some of them to 0. And then there's a Kaluza-Klein tower of other excitations. And then if I wanted to be very phenomenologically relevant, I could also, instead of compactifying on a circle, I could compactify an S1 mod Z2. And then I could pick distinct boundary conditions for the 4D vectors and the fifth components to project out states that I don't want in the 0 modes. So I'm going to ignore all of those for now, recognizing the things that I want to keep in my 4-dimensional effective theory will be the fifth component of the gauge field, the UN gauge field, and the vector component of the SUN. And I can pick boundary conditions so that I project out the vector component of the U1 in 4D, and I can project out any residual components of the.
But I think the question is, you can't write a theta term in 5D. That was the question.
Oh, no, I think that hopefully that's uncontroversial.
Because see, that might be allowed by the gauge.
No, it's why, you know.
Fifth components is,
The response theta is the fifth component of the U1 field, and so I was wondering why.
fifth components of SUN.
I could rephrase it as the question of why isn't the 4D theory a nonlinear single model, gauge nonlinear single model, which is naively what you would.
Absolutely. So the reason why good. So the combination of an appropriate choice of 5-dimensional gauge, which eats some of the degrees of freedom, and if you wanted to, a choice of S1 mod Z2 that projects out the fifth components of the SUN fields and the vector component of the U1 field would give me just these degrees of freedom in the IR plus the Kaluza-Klein towers of the SUN.
So it's coming because it's secretly.
They're not, well, it's not going, because it doesn't play an interesting role in the story that I'll tell you, and so you can either simply suppress it, or you can decide to delete it by choosing an appropriate.
Can I ask you something?
Yeah.
I'm embarrassed. So the top line is this 5 index anti-symmetry.
Yeah.
Is it also like the theta QCD can be written as a total derivative or not?
No, this is a genuine Chern-Simons term in 5 dimensions, right? I mean, you can move the derivatives around, of course, but
so if I just naively work in perturbation theory and I try to integrate the gluons, would this induce some mass term for the?
Well, the C is a dynamical field, right? It's not.
Would this generate hard breaking of C or not?
Sorry, would what generate a hard breaking C?
The loops of G.
No, I preserve, there's no, this is consistent with the U1 and the SUN gauge.
Yeah.
It's a Chern-Simons term.
It's a Chern-Simons term.
It's properly quantized.
So it's protected.
Yeah, I should say, you need this coefficient in appropriate units should be an integer to properly quantize. But it introduces no pathologies in the gauge symmetries. Okay, so why is this interesting from the perspective of the quality problem? Well, here I'm just going to quote Nima and company. They were actually considering this not for the purposes of the strong CP problem, but actually for generating an inflaton with a sufficiently flat potential, which is a very related problem. And they characterized this very nicely more than 20 years ago by saying that the extra component A5 of an abelian gauge field cannot have a local potential, and they invoke the higher dimensional gauge invariance. And they point out that although quantum gravity corrections may be present, they're negligible if the extra dimension is larger than the Planck length, distinct from a 4-dimensional scenario like we just described. And they emphasize that locality in the extra space is the key feature. That in some sense, virtual black holes don't spoil the gauge invariance, and they don't induce a local potential for A5. So anything that violates the shift symmetry of the axion has to be non-local, and therefore would be suppressed exponentially by, in some sense, the product of some 5-dimensional mass scale and the radius of the extra dimension. Okay. So this is why extra-dimensional axions are appealing from the perspective of the quality problem. There are no local operators you can write down in 5 dimensions that would violate the shift symmetry. So they have to necessarily be non-local effects, and those should be exponentially small. But if you think about it long enough, there are various things about this explanation that you should find unsatisfactory. One of them is that, if you're a particle theorist, you're sort of trained from birth that gauge symmetry is not a symmetry, but a redundancy of description. And so you would like to understand, in terms of the general and global symmetries of the theory, what actually is happening to protect the axion. It's also simply invoking extra-dimensional gauge invariance actually doesn't protect you against all of the effects that could gap the axion. For example, I could write down a Schnickelberg mass term, so a 5-dimensional abelian gauge theory. I could still write down a mass term for it and realize still some notion of gauge invariance. And the effect of this mass term actually would be to gap the axion in the 4-dimensional effective theory. So there's nothing about invoking gauge invariance that forbids this effect. And so somehow it can't just be gauge invariance that is allowing us to understand the protection of the axion potential. And then the final thing is, these these words here, they're very nice, but it's very hard to convert this into a systematic program. How do you know that you've computed all of the possible effects that could contribute to the axion potential? You need some sort of systematic language to account for what might give the axion a potential, et cetera. Okay. And so the motivation, that's what motivates now introducing the modern language of generalized symmetries, rather than maybe this historical way of invoking 5-dimensional gauge symmetry to understand why this is an appealing solution. The real thing that's going on is that the axion, of course, is protected by the 5-dimensional one-form symmetry, the genuine global symmetry of the theory. And just invoking that now allows us to systematically understand and enumerate why extra-dimensional axions are good solutions to some CP problem. I should say that this observation was first made by Matt Rees in his Tasi lectures, but not systematically expanded upon. Matt also subsequently followed up in a very related vein to what I'll talk about today to try to understand aspects of extra-dimensional axion quality, but not in the language necessarily of the higher form symmetries. Yeah.
Go back to slides about the 5D abelian gauge symmetry. I saw in this example, we don't have a abelian gauge symmetry. We're doing some non-abelian gauge symmetries.
Sorry, the axion is coming from the abelian gauge symmetry, and it's the abelian gauge symmetry that we're invoking to protect the axion. The non-abelian gauge symmetry is just a spectator because we want this to couple the QCD in 4 dimensions. Okay. Okay, so how does this work? So just the takeaway from this bit is that the axion shift symmetry in 4 dimensions really descends from the electric one-form symmetry in 5 dimensions, and the fact that, as we discussed, this one-form symmetry is hard to break, even if in the infrared, even if it's explicitly broken in the UV. This is the reason why the axion is very well protected. And so to see what's happening in the 5-dimensional theory, if we just think about, first, let's turn off the Chern-Simons coupling to the QCD-like sector. Let's just think about the free Maxwell theory. That has, again, an electric one-form symmetry whose conserved current is the field strength. It also has a magnetic symmetry in 5 dimensions. That's a 2-form symmetry, because the dual now is a 3-index antisymmetric tensor. And now if we ask what happens as we dimensionally reduce, as we compactify on the circle, the electric one-form symmetry now decomposes into an electric one-form symmetry of the 4D vector. If we kept that degree of freedom, if we project it out by a Z2 orbifold, then this would also be removed. And then it descends, the component for the axion is now the scalar 0-form symmetry of the axion. So the shift symmetry of the axion lives in the electric one-form symmetry in 5 dimensions. But I also emphasize the role of the magnetic 2-form symmetry under the dimensional reduction. Again, if we keep the 4D vector, that gives us the magnetic 1-form symmetry. But it also is what gives us the 2-form symmetry of the compact scalar. So, from the perspective of the EFT, we know that the axion has both a 0-form shift symmetry and a scalar 2-form symmetry. And in this extra dimensional picture, we can see it arises from the electric and magnetic symmetries of the 5D theory. Okay. Good. So that's just the symmetries of the Maxwell theory. Now, of course, you can ask, what are the effects that will break the symmetry? So in the Maxwell theory, these both symmetries are conserved by the equation of motion and the baryonic identity. But now that we've identified the real symmetry here, the genuine global symmetry that acts on the axion, we can systematically enumerate the ways that can be broken. So we can explicitly break it with matter charged under the gauge symmetry, as we're accustomed to thinking about explicitly breaking the electric one-form symmetry. We can break it with an anomaly term. So that's also a way in the presence of anomalies that we can break the symmetry. We can gauge the electric one-form symmetry. Now, that actually isn't breaking the electric one-form symmetry. It's making it an exact symmetry. But the consequence will be that the axion is no longer an axion. And finally, something that's surprising and very interesting is we can also, instead of gauging the electric symmetry, we can gauge the magnetic two-form symmetry. That will also give the axion a potential. In fact, it will give it a mass that we recognize as a monogeneous mass. Now, in the interest of time, I just want to go through these 4 cases somewhat quickly, just to convince you that this picture of using generalized symmetries to understand the axion quality problem really allows us to systematically control all the contributions to the potential. So the first example, we could break the electric one-form symmetry by adding electrically charged matter to the 5D theory. And so, of course, as we've commented, that now gives us a matter term on the right-hand side of the equation of motion. There's an invertible symmetry that remains, which is a ZQ symmetry, where Q is the charge of the matter we've introduced. And then you can go ahead and you can compute the potential this induces for the axion. Basically, the physical picture is now there are different contributions to the axion effective potential that come from charged matter winding around the extra dimension. And once we sum over all of those different windings, that gives us a periodic potential for the axion. But indeed, it has this exponential suppression that is proportional to the product of the mass of that charged matter and the size of the extra dimension, because that's what's setting the size of these Wilson loops that are wrapping the extra dimension. So this is an example where we had this very general discussion about the infrared imprints of explicit symmetry breaking of a one-form symmetry. This is now a very concrete manifestation of it. And the effects indeed have the form of e to the minus size of the Wilson loop times the mass of the charged particle.
Yeah. So what makes that cosine potential not aligned with the QCD cycle? Axion potential due to the QCD component.
Oh, that there can be phases from this which are not necessarily, if you simply add this to the QCD piece, there can be a phase in this, which is not the same as the phase in the QCD piece. There can be some delta, yeah.
Where would that come from?
It's the mass term. Is it the mass term of the charge?
Is it at all obvious? Sorry, you. So I see. If necessarily, sorry. You're saying if there can't be a relative complex phase.
Well, yeah, I don't see it immediately. That's all.
Yeah. So
Yeah, that's the question.
yeah.
Why it's not aligned with the cosine potential of axion?
Yeah. So good. I mean, I guess naively I would have said it's absolutely possible to have a phase between that you'd morally interpret as an offset between the instanton contribution and these charged particle worldwide contributions. It may be that you would have to think
it might come from your orbital. Like, you can interpret the orbital as a backdrop as a twist, and then that can introduce effective phase.
But he doesn't have it on the phone.
Well,
Well,
not here,
and yeah, so I think that's not relevant to the discussion. I think it is possible to have a complex phase, but that's not really essential to the discussion. In either case, you should be satisfied by the fact that these effects are exponentially small, given the size of the extra dimension relative to the mass of the charged particle. The anomaly piece, so in some sense, of course, we know there must be one anomaly piece, which is the thing that reproduces the QCD effect. So it's sort of obvious that the anomaly term also breaks the electric one-form symmetry. It breaks it down to some discrete subgroup that depends on the quantization of the Chern-Simons term. And then, of course, if we trace this down to low energies, this gives us the periodic potential that we used to from QCD. Although if we also sum over all the Kaluza-Klein modes, as Tony and others have emphasized, that can give an enhanced contribution to the axion mass, which is aligned with the QCD piece. Because those are all coming from the same components of the 5-dimensional SUN gauge field. I want to emphasize, so far, this is just a reprocessing of things that we already knew how to compute. But recognizing and organizing information this way also lets you compute new effects. So you can also, for example, have a Chern-Simons term that involved our U1 gauge field that has the axion in it with some other U1 gauge fields. Now, of course, normally that density of those other U1 gauge fields doesn't have any physical effects. But in the presence, for example, of monopoles of the other U1, those monopoles should give a contribution to the axion potential through the anomaly term. And in 5 dimensions, a monopole is a monopole string. And so you can go ahead and do a calculation of the contributions of monopole strings under another U1 to the axion potential through a Chern-Simons term. So it turns out you get a very beautiful result that mirrors quite nicely a calculation that was done a few years ago for the effects of monopole loops in 4 dimensions on an axion potential. But this is an example of a calculation which hadn't been done before, but it's suggested to you by organizing information in terms of the higher form symmetries. The other two cases, so to mention, you could gauge the magnetic two-form symmetry. And so that would mean you would couple some three-form gauge field to the conserved current of the magnetic two-form symmetry. At the end of the day, this turns out just to be what we would have called the monodromy mass for the axion. And so it gives a mass to the axion, which is not suppressed by any exponential quantities, but at least is proportional to an integer. And so if you would like to believe that we have a light axion in the infrared, that amounts to asking that this coefficient m here be 0. Okay. And then finally, you could imagine doing something which is not breaking the electric one-form symmetry, but instead gauging it. So that just amounts to now coupling a two-form gauge field to the two-form current of the one-form symmetry. But what you see when you go to the infrared, at the end of the day, you get effectively a four-dimensional Strickleberg theory where the axion gets eaten to become the longitudinal mode of a massive vector. And so although you've made the electric one-form symmetry exact, now there are no corrections to the axion potential. The axion is no longer a pseudoscalar degree of freedom that can relax to cancel the theta term.
For those four examples, do I still have the quality problem at all?
So good. So in fact, in giving you those examples, I haven't said anything about gravity, right? And we actually worry about the quality problem because we think these are Planck suppressed operators. So what's very useful about phrasing all of these ways of breaking the electric one-form symmetry or the magnetic one-form symmetry and giving the axion a potential is that now we can translate it into quantum gravitational expectations through various what we would refer to as swampland conjectures. So in totally parallel developments in the last decade, there's been immense development in sort of string phenomenology of the idea trying to make precise the notion, for example, that there are no exact global symmetries in the theory of quantum gravity. And that's given rise to a number of fairly sharp conjectures. I would say some conjectures are easier to believe than others, have more evidence for them. But some of the most robust conjectures that have come out of the swampland program are forms of what's known as the weak gravity conjecture, which is heuristically the idea that gravity is the weakest force. And this actually imposes very interesting constraints on effective field theories by simply asking that they be consistent, for example, with the existence and consistency of black holes. And so what you can do in this case is you can apply five-dimensional versions of these conjectures, for example, what we call the five-dimensional electric weak gravity conjecture or the magnetic weak gravity conjecture. And what this does is it tells you that there must be states present in your theory that carry charges that would lead to violations of the one-form symmetry. And it bounds the mass of these particles. And so that gives you a sort of minimum expectation for what quantum gravity should do in terms of breaking the electric one-form symmetry. So just to pick on one example to be precise, the five-dimensional electric weak gravity conjecture says that your theory must have dynamical electrically charged matter whose mass cannot be arbitrarily large in terms of the five-dimensional Planck scale. And the mass is bounded not just by the 5D Planck scale, but by the five-dimensional gauge coupling. So this is the statement, of course, that if I tried to make the five-dimensional gauge coupling very, very small, that would mean I would have to have a very, very light charged particle present in my spectrum. And of course, we know that it's these charged particles, they're loops that are giving us this contribution to the breaking of the electric one-form symmetry. And so this allows us to parameterize, we knew if I had electrically charged particles, the sort of potential they would give to the axion. And now we can say, in fact, there must be such particles present in the spectrum, and their masses are bounded in some sense by a relation to the five-dimensional Planck scale. And so this allows us to estimate, in some sense, the exponent in terms of the Planck scale. And what you find is, indeed, if there are electrically charged particles present in the theory that satisfy the five-dimensional electric gravity conjecture, then this was the e to the minus action that appeared suppressing those terms. Translated in terms of the weak gravity conjecture, that now gives you an exponent in terms of the Planck scale relative to the four-dimensional axion decay constant. And what you see is, because your potential contributions are suppressed by e to the minus m Planck over f, that as long as the axion decay constant is sufficiently smaller than m Planck, these contributions are exponentially small. So they regain, in some sense, the hope that contributions from quantum gravity are going to be exponentially small. And the reason they regain it is because it's coming from quantum gravity effects that break the one-form symmetry, which are exponentially small rather than polynomially small. You can apply similar arguments to some of the other effects that I've talked about. All of the effects that you get in this case are subleading to this one. And so the takeaway you should have here is that even if you ask what would quantum gravity do in this situation, it would give you corrections to axion quality problem that are exponentially smaller than the ones that we have in four dimensions. Okay, so what is the takeaway? Well, hopefully you at least believe that extra-dimensional axions really do provide a satisfying solution to the strong CP problem. And what generalized symmetries have allowed us to do is place the symmetry that protects these axions on very concrete footing in the language of global symmetries, and allowed us to completely and systematically articulate all of the ways in which those symmetries can be broken. But if you're a phenomenologist, I want to emphasize this isn't just sort of a satisfying bookkeeping exercise. it also points you to a lot of very interesting things that can happen now that have not been explored phenomenologically. So, for example, something that has been said many times over the last few years is that it would be too bad if you had an extra dimensional axion, because there's actually a way of producing these axions that would make them dark matter in our universe, where what happens is if the phase transition that breaks this Peccei-Quinn symmetry happens after inflation, you generate topological defects, axion strings, and the collapse of the axion string network gives you a very predictive amount of dark matter. Okay, a very sharp target for looking for the axion. But it's been claimed that, in fact, if you have an extra dimensional axion, because there's no Peccei-Quinn symmetry breaking transition, there's no extra dimensional axion strings. And this scenario is sort of precluded to you if your axion comes from extra dimension. But we've already said something, which is that if our axion is coming from extra dimensions, we can actually understand, for example, the two-form symmetry of our axion in the EFT as descending from the magnetic two-form symmetry of the 5D theory. Now, the charge objects under the two-form symmetry in the EFT are the world sheets of axion strings. The charge objects of the magnetic two-form symmetry are the world sheets of magnetic monopole strings in 5 dimensions. So this immediately tells you there are axion strings for an extra-dimensional axion. They just descend from monopole strings in 5 dimensions. And this is, again, an observation that has been missed in all the time that people have been thinking about extra-dimensional axions. And now you can study the phenomenology of these axion strings. So it turned out to be very rich. I won't go into detail here, but if you imagine, for example, your 5-dimensional theory that U1 that your axion was living in started inside as an SU2 that's broken to U1, then you would make Polyakov monopole strings. And now you can study what those do in the 4-dimensional effective theory, and they do a lot of very interesting things. Okay, so there is an entire story of post-inflationary axion dark matter generation from monopole strings in 5 dimensions, which we're only now beginning to work out. So that's an immediate phenomenological consequence from thinking about this in the language of generalized symmetries. Okay, in the last 5 minutes, I want to briefly go through the final part of my talk, which is a different phenomenological consequence that comes from higher form symmetries. And this one is really directly, intimately related to the standard model itself. And it's going to leverage something when I gave the sort of lightning introduction to generalized symmetries for particle physicists. We talked about explicit and spontaneous breaking. We didn't talk much about breaking via anomalies. And so I briefly want to mention some additional structure that we see in generalized symmetries beyond higher form symmetries in the presence of anomalies that has very interesting implications for phenomenology. Okay. So we already know, of course, even before we knew about generalized symmetries, we knew that anomalies were very interesting, either genuine ABJ anomalies or 't Hooft anomalies, because matching of things like 't Hooft anomalies across phase transitions allowed us to, for example, control the infrared structure of a theory, even if we didn't have control over the intervening dynamics. And the same thing is true when we have generalized symmetries, higher form symmetries, and now anomalies, in fact, have a very interesting effect where they sort of can mix generalized symmetries at different degrees. Now, in particle physics context, there's 2 typical cases. I won't go into great detail about them, but I just want to advertise them. If we have a theory that has some ordinary zero-form symmetries, for example, and a gauge symmetry, if there are 't Hooft anomalies that in some sense involve 1 insertion of a gauge current and 2 global currents, those are still 't Hooft anomalies and not ABJ anomalies. Then what happens actually is that the magnetic 1-form symmetry of the gauge group and the 0-form symmetries now start to mix, and they participate in what's known as a higher group. And just an example of what this mixing looks like is again, if you had just a UN gauge theory and a UN axial global symmetry, there's, for example, you could have a 't Hooft anomaly, which is 2 insertions of the axial symmetry current and 1 of the gauge current. And the consequence of this is that if you looked at the operator valued OPE, for example, of the axial symmetry currents, there would now be a contact term on the right-hand side, which depends on the current of the magnetic 1-form symmetry of this gauge group. So there's a sense in which the symmetries begin to mix in the presence of a 't Hooft anomaly. And I'll explain why we care about that in a moment. There's a second example having to do with anomalies, where if you have a genuine ABJ anomaly, then what happens to the global symmetries that participate in the anomaly is there's a real symmetry that's left over, which is a non-invertible symmetry. Again, this has been the subject of rich development in the last few years. And of course, in condensed matter contexts, dates back to well before that. But in 4 dimensions, it was worked out in a pair of papers a couple of years ago. And in the case of a non-invertible symmetry, there again is a mixing between whatever the anomalous global symmetry was and some higher form symmetries. So in particular, what happens if you had, for example, a real ABJ anomaly between an axial global symmetry and 2 insertions of a gauge current, the symmetry defect operators now change form. The truly topological symmetry defect operators become non-invertible in the sense that if you bring one of them together with what should be its inverse, instead of getting the identity, you get something that depends on the magnetic one-form symmetry that participated in the anomaly. Okay. So just to say, it's again a situation where the zero-form symmetry and the one-form symmetry begin to mix in the presence of an anomaly. And here again, unicorns should make an appearance. Why should I care? And the reason is something very interesting, something very powerful happens when these symmetries mix. So in many cases we've seen, especially higher form symmetries are emergent in the infrared at some energy scale. And whenever I have these higher symmetry structures, either in the case of a higher group or non-invertible symmetry, the scales at which the different symmetries emerge satisfy inequalities. They typically have the form that the higher form symmetries have to merge above the lower form symmetries. And okay, these are squishy inequalities. At the very least, they mean that the higher form symmetries cannot emerge parametrically below the scale of the lower form symmetries. And the intuition for this is whenever we have these mixing between the symmetries, the higher form symmetries are the good symmetries. The lower form symmetries have an anomaly, they're the bad symmetries. And it's inconsistent to have a regime in your EFT where you only have the bad symmetry without the good symmetry. And so that's what gives rise to these inequalities. And so this is articulated both in the case of the higher group and non-invertible symmetries over the last few years. And the reason why, as a particle physicist, we should care about this, as we've seen, particle physics EFT is rife with emergent symmetries and higher symmetry structure. And so these inequalities have to be satisfied in any UV completion. So if you have an EFT with a higher symmetry structure, any UV completion you write has to satisfy this. And that's a very powerful non-perturbative constraint on your model building. A lot was made of this a couple of years ago, where it seemed that there was interesting perturbative phenomena that was forced upon you by the emergence inequalities. I would say my perspective is that these inequalities are always satisfied automatically by some ingredients that are present in your theory. So for example, in many cases, there's something we've known about for decades, anomaly in flow. If I have, for example, a string object and some anomaly term, there must be charged zero modes that appear on the string. And that kind of phenomena assures that these inequalities are always satisfied. Okay, so it's maybe in the last year, I think we now understand this is not as mysterious as it seemed when this position was originally articulated. But what I want to use the last couple minutes to tell you about is, even though these inequalities are satisfied by some non-perturbative phenomena that we've known about for years, the language of higher symmetry structure allows us to understand where these effects should appear, and it points us to phenomenology that we haven't been paying attention to. Okay. So just to give you a concrete example in the standard model, the standard model actually has a lot of higher group structure. In particular, if you turned off the Yukawa couplings of the standard model, we know we have enormous global flavor symmetries associated with rotating fermions of different generations into each other. And many of those global symmetries actually have a 't Hooft anomaly with hypercharge. So they participate in this two-group flexion. Okay. And so you can ask, well, what happens? I have this emergence inequality. It tells me there's a magnetic one-form symmetry of hypercharge. And if that emerges at some scale, the flavor symmetries that participate in the anomaly can only emerge at a lower scale. Now, this was used to very good effect by Clay and Seth a couple of years ago. They considered, in theories of grand unification that unified the standard model gauge group, very often unification gives rise to monopoles. Those monopoles would break the magnetic one-form symmetry of hypercharge. So below the scale of the monopoles, the one-form symmetry emerges. And now applying this emergence inequality that tells you many flavor symmetries of the standard model can only emerge below the scale of the monopoles. Equivalently, this allows you to determine immediately what are the ways you could unify standard model fermions into a grand unified group that produces monopoles. So that's reproducing something we've known how to do for a long time, but it's a very interesting way of rephrasing it in the language of generalized symmetries. But what I want to point out, when they did this analysis, they were thinking about the gauge bosons of the unified gauge group as imposing this constraint on the flavor symmetries. But just as I've already told you, usually these emergence inequalities are satisfied by non-perturbative phenomena. So you should ask, what's the non-perturbative effect that guarantees the emergence inequality is satisfied? And in this case, where you have a two-group symmetry, the non-perturbative phenomena is monopole catalysis, right? It's the Kalin-Rubikov effect. In fact, so this is again something we've known about for a long time, originally in the case, for example, of SU5 grand unification, where it's observed that baryon number can be violated in scattering off of SU5 monopoles. And the picture that people had back then was, well, certainly, if you have fermions that penetrate into the core of a monopole, they see massless SU5 gauge bosons at the core, and those SU5 gauge bosons mediate the decay of the proton. But I want to emphasize this phenomena has very little actually to do with the fact that there are massless unified gauge bosons at the core of SU5 monopoles. It's just a natural consequence of the fact that there is a higher group structure here. So in fact, if you want to know what global symmetries are broken by the Kalin-Rubikov effect and scattering off of monopoles, any global symmetry that participates in a 2 group is going to be broken by the Kalin-Rubikov effect. Okay. This was very nicely framed by David Tyne Zohar a couple of years ago. And so this allows us to understand how we interpret these emergence inequalities for a 2 group. Necessarily, these flavor symmetries are broken and scattering off monopoles. Okay. The reason I mention this to you is, so although indeed the standard model has a rich higher group structure, it also has a rich non-invertible structure. So many abelian flavor symmetries of the standard model participate in ABJ anomalies with both hypercharge and SU2 left of the standard model gauge group. And so, of course, it's absolutely true that these anomalies, and then also, of course, with QCD, the anomalies with SU2 left and QCD break many of the U1 flavor symmetries. But some of the residual flavor symmetries of the standard model are genuinely not invertible. And we can also still carry out the thought experiment that even if you turned off the SU2 and SU3 gauge couplings, hypercharge would still render these symmetries non-invertible. And so we should be able to apply the logic of these emergence inequalities to look for new phenomena that we might have missed. Okay. In particular, any flavor symmetries of the standard model that participate in an ABJ anomaly with hypercharge should necessarily be broken and scattering off of monopoles. Now, we know that that happens for SU5 monopoles and SO10 monopoles. We've known that for 40 years. But I want you to think for a second about more interesting unified gauge groups where baryon number is actually a good global symmetry of the classical theory. So an example of that is Patti-Salam grand unification, where lepton number is the 4th color. So that unifies the standard model gauge group in an SU4, SU2 left, and SU2 right. And baryon number is an accidental symmetry of this theory. Okay. So U1B minus L is actually a gauge symmetry. U1B plus L, the other linear combination, is an accidental symmetry. And so classically, the gauge bosons of this unified gauge group do not mediate baryon number violation. But we've seen, right, so this combination B plus L participates in an ABJ anomaly with hypercharge. So in some sense, it's non-invertible. And that means if we have monopoles, for example, monopoles of the Patti-Salam theory, those monopoles should also catalyze baryon number violating processes. Okay. But it turns out the baryon number violation is much more interesting than it was for SU5, because the electroweak anomaly of the standard model doesn't break B plus L entirely. It breaks it down to a Z6 subgroup, where one of the factors of 3 in that Z6 is actually the number of standard model generations. So it breaks it down to a discrete subgroup that knows about the number of families in the standard model. Okay. And so it should be the case, we would expect that if we scatter baryons and leptons off of Patti-Salam monopoles, because of this non-invertible symmetry structure, it should violate baryon number but preserve the Z6 symmetry. And those sorts of processes are very interesting. They're the same processes that we expect from electroweak sphalerons. In other words, they change baryon and lepton number both by 3 units. And this sort of forced upon us by the generalized symmetry structure theory. But actually, there's a completely unknown paper by Ashok Sen from 1984, where he actually calculated a baryon number violation in scattering off of Patti-Salam monopoles. He didn't have a systematic framework for understanding what the effect should be, but he did know that in the presence of an electroweak anomaly, there should be violation of baryon number and scattering off the monopoles. And indeed, he found, although he didn't have a systematic way of describing it, that the non-zero processes were delta B is equal to delta L is equal to 3. Okay. And this is extremely interesting. So why is it extremely interesting? We really, if you take a particle theorist off the street and ask them if they believe that there's gut monopoles traveling through the universe, they would say absolutely not. And one reason they would say absolutely not is you can ask what's the state of experimental knowledge of the presence of monopoles. You can parameterize it as a function of, say, the monopole velocity through the universe and the flux of the monopoles. There are a variety of bounds that come from terrestrial experiments or indirect things like the persistence of magnetic fields in the universe. So these give relatively weak constraints on monopoles. And then there's dramatically stronger bounds by about 10 orders of magnitude, which come from if we have a grand unified monopole, some of them will get captured, for example, in the sun, and they would sit at the middle of the sun. And if it were an SU5 or an SO10 monopole, they would catalyze baryon number violation. They would just be decaying protons, making neutrinos, and then we would look for that spectrum in the superconducting experiment. And the fact that we don't see that spectrum of neutrinos gives us a bound now that is dramatically stronger than all other bounds in monopoles. But these bounds rest on the assumption that the monopoles are catalyzing delta B is equal to 1 processes. And what I'm telling you now is there's a much more interesting situation where the monopoles could be sitting in the sun catalyzing delta B is equal to 3 processes. The bounds are in principle much weaker. We don't actually have any good searches in any experiment for delta B and delta L is equal to 3 processes. And so this is just completely uncut grass when it comes to looking for experimental signatures of monopoles whose baryon number violation is dictated by the higher group structure. I should say, I've focused on this example of Patti-Salam monopoles, but again, the emergence inequalities tell you that any monopole, whether it's coming from a gut or anything else, that inside a piece that's it's proportional to hypercharge, will also catalyze these processes. And so, there's just a huge array of phenomena with this high number violation of baryon lepton number in the presence of monopoles at any scale that we really haven't looked for experimentally. And so this is something that we should do because, a lot of particle physics has been about looking at problems of the standard model, hoping that nature solves them, and then looking for signatures. But we could take a very different perspective, which is if we just look at the standard model, its anomaly structure in the infrared tells us about a lot of very interesting things that can be happening in the UV, and we should just go about looking for them. Okay, I apologize for going a bit over. Hopefully I've convinced you that generalized symmetries are interesting for particle physics, both in the standard model and beyond the standard model. I think it's very much true that we're in early days of understanding what they can tell us. I've tried to give you 2 concrete examples. One of them is thinking about how we can use it to understand high quality axions for the strong CP problem. The other one is very phenomenological, which is just pointing out that there are processes mediated by monopoles that we really haven't looked for. But we are now awake to them because of the organizing structure of generalized symmetries. So thanks very much for your time.
For the 5D model that you had of the axiom, what happens if I was to add a higher dimension term to my 5D theory, right? So I add some higher dimension term that breaks CP.
On the brain.
In the bulk, for instance. Because it's a gravitational theory, right? Or
so none of those, any such terms that I would write, right? Those, there's no local, those operators don't violate the one-form symmetry. So they would not give a potential for the axiom. Once you boil it down to the 4-dimensional effective theory and compute the axiom potential, even though there's a CP violating term, that local operator, right, that doesn't do anything to the one-form symmetry.
Because I was thinking of adding something like a high dimension gauge field term, if you knew tilde, something like a Weinberg.
But you need a condensate. Yeah, no, but so that term alone, now the one-form symmetry current, where you would just redefine it. This is also true of kinetic mixing. You could have kinetic mixing, but there's still a conserved one-form symmetry. So any local operators you add just move around what you call the conserved current, but they don't break it. Now there's a related thing you could have worried about, which is, so nothing in the 5D bulk will break the one-form symmetry. But you might worry that what if I had an S1 mod Z2, and now I could write down 4-dimensional terms on the boundary that could break the shift symmetry. But actually, the one-form symmetry is powerful enough to forbid that as well. So this is explored. There's a paper written by Quiros and collaborators from 20 years ago that we should rewrite in the language of generalized symmetries. But they find, they don't really understand what's going on, but they describe an infinite tower of constraints that come from the 5-dimensional gauge symmetry that forbid dangerous effects from boundary localized terms. Okay, and so of course now we would say that's just a consequence of the bulk 5-dimensional one-form symmetry, and in some sense some brain to bulk volume effect.
But this is just in flat space. It was just
That's one mod Z2, yeah, flats with that, yeah.
This
So
is Quiros paper.
yeah.
Why not add a massless charge fermion in the 5D?
Oh, well, indeed, of course, if such a degree of freedom were present, then of course your quality would be ruined. So, but the important thing here is, right, we know that quantum gravity requires sufficiently light charged fermions, but it does not require them to be so light that they demand that the quality is broken. So of course, just as with the gauging the magnetic 2-form symmetry, of course, if it is gauged and the coefficient is not 0, right? So if it is gauged non-trivially, then of course the axion is also lifted, right? These effects could be present, but the fact is they're not required to be present. And so, whereas electrically charged matter of some mass is required to be present, so that implies at least the minimal breaking.
For the magnetic gauging and electric gauging, I still have a quality problem. right?
Well, for the electric gauging, you don't have a quality problem. The axion has no potential. Okay.
Oh, yeah, sorry.
Yeah,
For the
okay.
magnetic gauging.
For the magnetic gauging, well, good. You would again have to ask, there's this question of, is there an additional complex phase? So certainly there's a potential. Mostly you would just, you would worry. It seemed to me, I don't see why there couldn't be a relative phase between the QCD piece from the instant ion contribution and magnetic gauging piece. And in the presence of such a phase, indeed, this mass term would misalign the vacuum from the QCD.
Oh, I hope we don't, but then I can have a heavy axiom for that.
Yeah, so then it would be a question of, is there a natural way to understand the alignment between the heavy axion potential and the QCD potential without a relative phase offset? Which, potentially is something that would be interesting to do in 5 dimensions, but it's not obvious to me why you can forbid it. Yeah.
So about the monopoles that you mentioned near the end, very naively, I thought monopoles were all supposed to be inflated away.
Well, so of course, certainly the natural thermal abundance, the production of topological defects in the early universe, we know the energy density from those monopoles would dramatically overclose the universe. So inflation does have to get rid of them. The question is, how much did inflation get rid of them? So it is still absolutely possible to have a monopole flying through the universe and park itself in the sun without having overclosed the universe. Now, on this plane, so that there's a reason why these bounds, right, the most productive space in which to plot them, the experimental sensitivity and these phenomena depend on the velocity of the monopoles, right? And it depends just on the flux of the monopoles. Now, any particular early universe cosmology lives at some point in this plane. Right? So, of course, inflating absolutely everything away with arbitrarily many e-folds of inflation, your flux is down here.
Right.
But
you don't have to do that. Your point is you don't have to do that.
You don't have
also imagine that they're produced after inflation, that the gauge symmetry is
Right.
preserved during inflation.
Right.
And when inflation
It's not some
ends.
reheating or something or whatever.
Not even a question of reheating, it's just,
the kibble, yeah.
well, it depends on whether or not your gauge symmetry is broken during inflation, whether the dynamics of inflation are such that gauge symmetry is broken. It could be that, the way inflation works, it forces the symmetry to be preserved during inflation and only breaks afterwards.
That makes sense.
And I want to emphasize,
Of course, that would normally give you a huge problem, so
Right.
you normally don't want to do that.
But I want to emphasize even monopoles that are in some sense not topological defects. So you could have a Dirac monopole, like just a normal Dirac monopole. And as long as in some sense, it as a normal monopole, it has a piece in the hypercharged direction of the standard model gauge group.
Yeah.
And in the presence of the electric anomaly, that Dirac monopole also mediates these delta B is equal to delta L through the 3 processes. Right? And so there's nothing wrong with some abundance of Dirac monopoles of mass much less than the gut scale. So that absolutely could also live in this space. Right. So it's I mean, I think the thing not only Sen knew about Paddy-Slom catalyzing these delta B, delta L3 processes in 1984. That paper has 8 citations. I think it qualifies as not well known. But then this additional point that even without, that was the historic thinking that at the core of these monopoles, there's some gut gauge bosons.
Yeah.
But now recognizing the language of generalized symmetries, that even if it's not some solitonic polygon monopole, the presence of the anomaly plus the monopole mandates these effects, means that there are many more situations in which this should also occur.
Why wouldn't this monopole in the center of the sun not self-annihilate? Presumably they're both signed, right?
So indeed, I think when they do these, when they set these limits, right, there is some assumption about what so there's some assumption as a function, obviously, of the velocity and the flux of the number of monopoles and anti-monopoles that would be accumulated over time, the ones that would get rid of each other, the ones that would stick around. So I think in these curves, there are some possibly reasonable assumptions about what as a function of the flux and velocity distribution, the number that persists to catalyze at any given moment the proton decay.
It should be an equilibrium number that's like dark.
Sure,
Yeah, they would not be
If
guaranteed
you
to.
annihilate too many of them, they'll reaccumulate, right?
no, the flux from the outside is.
Yeah, I think this effect, as you can see, is driven by the flux from the outside.
Fixed.
Yeah.
But what,
So there should
yeah,
be some.
like, if I have 1 or 2 monopoles, that's certainly not enough to see from the neutrino.
Well,
So
I
it
mean,
has to be some
it's
sort of
it's
population.
catalyzing proton decay with a geometric cross section in a relatively proton-rich environment.
And
So I think even a
this
small
is,
number of
this
them.
is such a tiny thing compared to.
Well, but it's also a very distinctive spectrum, right? So so absolutely the calculation.
Not flux by
Sure.
any
So-
measure. It has to be like a population.
Yeah, which is absolutely why, of course,
But that's where the limit comes from.
yeah, I mean, that's,
Sure, no,
that's,
but
yeah,
what I'm
which is,
saying is that.
right, which is, yes.
One has to take into account that they self-attract because they have a different.
Absolutely. So
And
my,
they can annihilate.
my understanding is the super K prediction.
Very large cross section.
So at least as I think the calculation, the super K constraint is from 2012. I think the underlying prediction is from the 80s. So my understanding is this was understood then, but you know, it would also be very useful to the extent that we become interested again in observable effects from monopole populations in stellar objects. Absolutely, making sure that we completely understand the abundance in the objects is a very useful question. Hopefully, I've motivated you to think about it. Yeah.
Given gauge theory, is spontaneous breaking of electric symmetry, is that scale independent thing? Like it's just an intrinsic thing given the gauge theory. So we cannot discuss anything about the energy scale where it's spontaneous breaking of electric
No. So I think the analogy is because it's broken in the Coulomb phase. If you imagined undergoing a phase transition, say from a confining phase to a Coulomb phase, that would be what you would call the scale of the phase transition. An analogy with the scale of a spontaneous breaking of a zero form symmetry.
And Nathaniel, that here in this extra dimensional axion scenario, like wouldn't that give you the this scale where the axion string generally gets generated?
Well, so in the example I gave you where the monopole strings are just Polyakov monopole strings,
Yeah.
the scale where they get generated is the scale of breaking of SU2 to U1. You could also imagine a scenario, this is less well worked out, where maybe you're in 5 dimensions and you have a gas of monopole strings. And so then in some sense, you're in a confining phase of the U1. And then you go from the confining phase to the Coulomb phase. And at that point, you spontaneously break
And
the
axion gets generated. It's not most Boson of the electric.
and then it becomes exactly. So that would be another way of thinking about a phase transition. But what I had in mind for the string formation was just an SU2 to U1, and then it's a Polyakov string formation. But I think the analogy for higher form symmetries for what is the scale is the transition into the Coulomb phase, which can happen as a function of scale. That is the closest thing.
Yeah.
I don't know if you would disagree, but
Sounds great.
Yeah.
Okay, I think it may be good to
Yes, sorry.
close the.
Taking
first
quite
part of
long, I'm
this
sure
and
you'd
then
all
let
like to
Deepak
go.
Chase you.
So,
to
thank
the-
you very much.
Okay, thank you.